what we were talking about. Remember, in section 1.4, we're putting together what we previously know about continuity and points of discontinuity, and then kind of putting that together with now our knowledge of limits. And we're able to come up with this better definition of continuity, or what it means for a function to be continuous at a point, as well as continuous on an interval, right? So for continuity at a point, you can think of this almost like a checklist. Like a function will be continuous at an x value if the function is defined at that x value, if the limit as x approaches that x value exists, but also if the limit is equal to the function value, like the limit and the function value match. If any one of those criteria fail, then the limit is not continuous at that point. And the reason you would still want to think about that definition is that through applying that definition, you can determine what is actually happening to the function. Like you can tell, even if the function is discontinuous, like how that definition fails can tell you about like what is actually happening. Like if there's a removable versus a non-removable discontinuity, right? A whole versus the function value is something other than the limit value. If the limit doesn't exist, like how it doesn't exist could tell you if there's a jump in the graph or if there's a vertical asymptote, which some of this we'll have to wait until 1.5. We've completed 1.5 to kind of close the circle on being able to identify all of those characteristics, but like this is a good starting point for us. And then for continuity on an interval, right? So thinking about like the fact that this definition has to be true for every value that's on an interval. We'll talk about what happens at endpoints in a second here. And then remember, for types of discontinuity, so if there's a point of discontinuity, it's either going to be removable or non-removable. If the limit exists as x approaches the x value, so as x approaches c, then that tells you that the function has a removable discontinuity. Previously, we've described a removable discontinuity as something like graphically, you could think about just filling in that point, like removing the discontinuity just by filling in a single point. If the limit does not exist as x approaches c, then that tells you that it's a non-removable discontinuity, which would either be from there being a jump or from there being a asymptotic behavior, right? So a vertical asymptote, the function either approaching positive or negative infinity as x approaches c. We had discussed the continuity of this function. Remember, we had to, in order to get the discussion going, we kind of have to rely on our prior knowledge. So we're going to go through a couple other functions and discuss their continuity. And like, if there is discontinuity, like look at what happens applying that definition of continuity at a point. I know I've ruined the surprise by telling you there's a non-removable jump discontinuity here, but kind of ignore that for now. G of x is what type of function? It's a piecewise function, okay? It's a piecewise function. If we look closer at the rule for each piece of this piecewise, like negative x and x squared are both polynomial functions. Polynomial functions you guys are familiar with, and you know that polynomial functions are continuous over their implicit domain. We know this, yeah? Right? Like, meaning you could trace a polynomial function over its implicit domain of all real numbers, and you would never have to lift your pencil. But because this is a piecewise function, you're like, oh, there actually could be potentially a point of discontinuity where the domain switches. So we are going to focus our discussion in on x equals to 2. Do we follow that? Like why we're thinking about x equals to 2? So we're thinking, is G continuous at x equals to 2? And again, the reason we are focusing on 2 is this is where the domain switches or changes. So using the definition of continuity, we're first thinking, well, what's G of 2? What is G of 2? 4. And we decided to plug in 2 into the x squared because, yeah, 2 is included in this interval, right? So at the moment, pretending that we don't see this spoiler, you're like, oh yeah, G could be continuous at 2. Could be, right? And then we're like, okay, well, let's find the limit. We're going to that second item on the continuity at a point checklist, which is, does the limit exist? Well, if we thought about taking the limit as x approaches 2, our go-to is normally direct substitution, right, first. However, because this is a piecewise, where the function changes rules at 2, we must consider the one-sided limits. We must consider the one-sided limits. So we go, okay, the limit as x approaches 2 from the left of g of x. And we're also going to think about the limit as x approaches 2 from the right of g of x. If you were being explicitly told, remember I told you to not think about how something would appear in an assessment for these questions because we're just having a little discussion about the continuity. If you had an assessment question that explicitly asked you to use the definition of continuity at a point to justify if the function was continuous or not, you would want to make sure when you're taking these one-sided limits that you are referencing the function g of x. It would be incorrect to show, oh, the limit as x approaches 2 from the left of negative x, and then the limit as x approaches 2 from the right of x squared without referencing g of x before that. And maybe I'm getting a little bit ahead of myself here. But the reason I mention that is because when we take the limit as x approaches 2 from the left, you're looking at the rules of the piecewise and you're like, oh, values to the left of 2 would be in this interval, right? So you would want to end up thinking about applying direct substitution to negative x, right? Like you're plugging in 2 into negative x. Just reference the piecewise by name. If you wanted to, you could say, and this is not required here, I'll use a different color here. You could say that, oh, this limit is equal to the limit of negative x as x approaches 2 from the left, and then show direct substitution, but you don't have to do that. I would actually probably avoid it. Just to not actually use incorrect notation. Okay, so we end up with negative 2. And then as x approaches 2 from the right, okay, values to the right of 2 are in this interval, right? So we plug in 2 here and we would get 4. Which, putting that together, since the limit as x approaches 2 from the left of g of x is not equal to the limit as x approaches 2 from the right of g of x. That means that the two-sided limit is, the two-sided limit would be dne. Because the limit is dne, we can say that means that g has a non-removable discontinuity at x equals to 2. If necessary, we could figure out like what graphical manifestation occurs at 2 based on how that limit failed to exist. Right? Like you guys could tell me what occurs at 2 on this graph. A jump. Okay? And I realize you're thinking, well, I would have been able to tell that before, but like explaining that and justifying that would have been difficult without the limit language. So the reason that there is a jump in the graph is because the limit as x approaches 2 from the left is equal to a number, and the limit as x approaches 2 from the right is equal to a number, but those one-sided limits aren't equal to each other. So that tells you that there would end up being a jump. So if we wanted to go a step further, because if you know about a discontinuity, a point of discontinuity, you can also rely on your prior knowledge about these different types of functions. And we could also make a statement about like where g is continuous, couldn't we? Like we could say that g is continuous on the, and I'm going to stick to open intervals for now. We will eventually be able to use a half open interval for one of them. But g is continuous on the open intervals -infinity to 2 and 2 to infinity. What? Are they playing music down there? I feel like I just like block it out. I don't even hear it. It's like white noise in the background. Okay, so questions about this piecewise function, how we determine point of discontinuity, or the intervals where the function is continuous. Now I hear it.
So what's the symbol for and again? It's like the U, right? Wait, that's the U. We can't do it.
I'm just listing them. I would not. Some texts would. I would not. I would just list them. Okay. So let's focus in on this rational function now. So remember how the last time I was like, hey, let's put a pre-calc brain on for a sec. So putting our pre-calc brain on, if I presented you with this function and I started asking you to identify characteristics about this function from a pre-calc or an algebra perspective, do you have a question?
No, observation.
Okay, hold the thought. If I asked you to start identifying characteristics from an algebraic or pre-calc perspective, the first thing that you would probably do is identify a domain restriction. Like just looking at that equation, you would probably identify a domain restriction, or it would be at least one of the first things. Kyle, would you like to comment on that?
Yeah. Was a discontinuity at x is equal to -2.
Well, don't talk about discontinuities yet because we haven't applied any sort of definition relating to continuity yet. But to get us going on our discussion, we could at this point identify that the only potential point of discontinuity would occur at the domain restriction, which is that x cannot be equal to -2, right? Like if you were listing the domain, you would say from -infinity to -2 union -2 to infinity, right? We'd exclude -2 from the domain. So that's where we can focus in on applying that definition of continuity at a point for this function, is we're thinking like, what is happening to h at x equals to -2? And using our definition of continuity at a point, we can figure that out. So we could think, first of all, h of, and we already knew this, right? H of -2 ends up being 1/0, which is undefined. So right away, right, we go red flag, we know discontinuous at x equals to -2. But we want to investigate a little bit further to say, is this a removable discontinuity? Is it a non-removable discontinuity? If it's non-removable, is there a jump? Is there a vertical asymptote? Like, what's going on with the graph of h from a calculus perspective? I know that you guys, you're used to doing it kind of the backwards way for actually why the graph is the way that it is. But we want to use, now that we have limits in our toolbox, we want to use that to help us have like a real justification for what's happening to h at -2. So right away we're like, hey, h is not defined at -2. We knew that from our pre-calc brain, right? And then we think about the limit as x approaches -2 of h of x. And because with direct substitution, we would end up with 1/0, right? Like a non-zero number, real number over 0. Like that tells us the limit doesn't exist, right? Like it's not a whole case, a potential whole case, right? Or removable discontinuity. Like it's just the limit is DNE. Because that's what you would end up with from direct substitution. Now, in section 1.5, we would be exploring this further, and we would be like, oh, the limit as x approaches -2 from the left, and the limit as x approaches -2 from the right. Like, what's happening? And because 1/x plus 2 is one of those functions that you should be able to visualize the graph, right? 1/x, the parent function, and then the plus 2 does what to the graph? Left 2, right? So as x approaches 2 from the left, -2 from the left, h of x would be approaching -infinity and +infinity from the right. So really, this DNE is all we could say. But because the function is increasing or decreasing without bound as x approaches -2 from at least one side, we can conclude that there is a vertical asymptote at x equals to -2. And again, I'm putting this in green because this is really in section 1.5 what we'll focus on. But for now, because this limit, what just happened? Because this limit was DNE, we can say, therefore, h has a non-removable discontinuity at x equals to negative 2. We could also say that h is continuous on the open intervals from negative infinity to negative 2 and negative 2 to infinity.
We need to write this in like every problem.
Remember I told you you should not be thinking about assessments. We are having a discussion about the continuity of this function. This is not a question that would appear on an assessment, at least not this exact wording. That's so open-ended.
I feel like homework.
I can't remember. Is it okay to move on, you guys? We have talked about one-sided limits. Now, your textbook technically doesn't introduce one-sided limits until this section, which I think is funky, and that's why I have already introduced one-sided limits to you, because I think it's weird to talk about two-sided limits, and also two-sided limits that don't exist if you're not talking about one-sided limits, or don't know what a one-sided limit is. So, we've already talked about one-sided limits. You guys know what they are, right? Left-hand limits, right-handed limits. But one-sided limits are also going to allow us, right? They help us with determining if the limit exists or not. But they're also going to allow us to discuss continuity on closed intervals. More specifically, they'll allow us to be able to discuss continuity at the endpoints of intervals. Okay. So we will be able to say that a function is continuous on a closed interval or a half open or half closed, depending on how you look at it, right? Like basically what's happening at the endpoints of an interval, if the endpoint is included, by relying on that definition of continuity at a point, that because we're talking about the endpoint of an interval, we are allowed to just consider a one-sided limit. So, a function f is continuous on the closed interval from a to b. That means a and b are included in the interval. When f is continuous on the open interval from a to b, that's same as before, right? Like, so that definition of continuity would apply to every point on the open interval. But for the endpoints, we would be able to say that the function is continuous if at that first endpoint, the limit as x approaches a from the right exists and it matches the function value at the endpoint. Which goes back to definition of continuity at a point, right? Except for we're just considering a one-sided limit because we're at the left endpoint of the interval. Do we follow that? And then same idea, but for the right end of the interval, the right endpoint of the interval, if the limit as x approaches b from the left matches the function value at the endpoint of the interval, then the function is continuous at that endpoint. And we can think of this as being true for like half open and half, like on either side of a half open interval. We are going to skip this example for now. If you wanted to peek at it later, you could. But what we're going to do next, please don't do this yet because you don't have all the directions for it, is I am going to ask that you state the intervals where the function that's in the graph is continuous. So that could be open, it could be closed, it could be half open intervals. And I also want you to specify the x values where there are removable discontinuities. Don't start yet. And the x values where there are non-removable discontinuities. So I'm going to have you guys do that in groups. Why don't we do 3, 3, 2. So talk to your group members, read the graph. When we're talking about intervals, we're talking about intervals of x values. You're reading the graph from left to right, determining the intervals where the function would be continuous. You're considering endpoints of intervals and if you would include it or not. And think about, like, could I explain? Check with each other, like, can we explain why we would include an endpoint, why we wouldn't include an endpoint? Okay, so why don't you guys shift your desks so that you guys can clearly communicate with each other? Yeah. You guys turn so you guys can communicate with Julianne.
Oh, that's negative.
Kyle, you're with them. I mean, you can be with them if you prefer.
Also continues from negative 6.
Pull your chair closer. I'm just going to here. Sorry.
2, but not
Let's
all.
start at negative.
None of them are
Negative 2.
2.
So do we include that one dot? One for right? Yes.
Oh wait.
Yeah.
Yes. Would we start on continuous? Would we start on continuous?
It is to the left, to the right of it. So it's not.
I actually don't think that's good. I think you're wrong
How can there be?
because this is also linear.
Yeah.
Because this is a piecewise function. The asymptote's only for this part. Actually, non-stable.
Yeah, I'm doing this. I'm just checking which are included.
And if I needed to,
None of them are included.
Negative 2.
5 is
I like
included
it.
because it goes 2.
Literally not.
How does this look?
5 is included.
Wait,
Five.
are we including those
Yeah,
like
6.
points?
2.
No, to 5.
Wait, are you guys including the floating points?
5.
No, I think that's not continuous. Because the limit. What's the limit here?
The dots wouldn't
What's
count
the
as
limit in
continuous.
2?
Other than that,
It's removable.
That doesn't bro.
At
Lock in.
no, it's not.
no, because that's like.
Would we include those, just the floating points? Like these?
It would be
Wait. Is
no, but
negative 2
I
removable or removable?
negative 2 x equal negative 2 would also be.
It's.
Yeah.
Yes.
Yes.
It's like.
So why would you
Is
say
it acid?
Oh no, I just yeah. I'm being so honest. I didn't do
I-
1 and 2.
2.
No, just
2. 2.
But you would include this point, right? Yeah.
So you guys have,
5 and 6.
X equals 6 is also
you guys don't want to just like read off our stuff?
negative 2, right?
Yes.
There's a
And
mental
then
asymptote and like
6 to 8.
Okay.
So.
Yeah.
Alright.
But it's
Still not.
8 is
Ready to get jumped. Yeah. Wait, the jumps are.
But then the
Jumps
eight.
are. Jumps are not.
No, it's just 8.
No, lads.
There's just
Oh, whoa, bro. Locked in. My bad.
And then 8.
I thought you were trying to say 18.
Branch removable.
You're the way to go.
Wait, so
They want us to do union for
11 is removable.
no, right?
I would just,
Wait, 11?
I would just list them. I separated with a comma, but,
Up here.
or you can just list them.
No, it's not.
Wait, it's, no, wait, no, it's jump.
Wait.
11 is 2.
Okay, one more minute. We're going to check in.
No, it's a job.
Find the infinity. Yo, find the infinity on the graph.
Okay, yeah.
Alright,
So
what's remove one?
Yes.
What about 11?
What you guys get for removal? I got x equals 8 and x equals 10. 8? I got negative 2, 5, Alright, asymptotes. Wait, no, asymptotes. Oh, wait. Wait, so it's just.
Whoa, I wonder where we got this from. Yeah, I know, right? Very mysterious.
Wait, how is 8 removable?
No one knows where I got.
Not like it. I'll quickly stop.
It's a secret. Thank you.
Well, cross country is funny, then you should.
I feel like the white one that we know.
0.1.
The person just that really sells it. You vibrate that product.
3 miles.
30 miles.
Me and my mom got
That's
matching
like-
notes, that's all.
Exactly.
That's like 2-point-something kilometers.
It's not a
It's
dance
like
thing.
5 kilometers.
He's like,
Use
the cursive really.
30 miles, yeah.
No, underneath it would have to say live, laugh, love. You know?
Did you wear this this week?
It's like
5.
I would.
Or you could have one of those like.
What is cross country?
You run just outside. You run
Oh, yeah. They were always
I almost feel like that's a little old lady-ish.
But it's like right
I hope. Oh, you're not running it.
Or put like an infinity symbol underneath it.
Yeah. On his bike.
Alright, you guys, let's check in. So, reading the graph from left to right. Okay, so thinking about from your pre-calc perspective, you could be thinking about where would I be tracing the graph. So from negative infinity up to it looks like negative 2. Would we include negative 2?
No.
No, why not?
Because there's an asymptote.
There's an asymptote. Did you guys notice that the function actually is defined
Yes.
at negative 2? But because the function is approaching positive infinity from the left, well, there's no way that that limit, that one-sided limit would match the function value. To kind of go back to that definition. Okay, and we can't talk about continuity, like, unless there's an interval around it, then you can't consider the limit, right? So we're not talking about at a point. So then we can move on and go for the same reason.
But we don't include points in continuous.
Well, you can't take the limit,
Oh, okay.
right, as x approaches.
Yeah.
Okay, so then we go from negative 2. We are not including negative 2 for the same reason. But now thinking about the right-sided limit. As x approaches negative 2 from the right. And then we can trace. We get to 2. Would we include 2? Why not? Because I said so. Why wouldn't we want to include 2? Use the definition, you guys. It's not a hole.
The limit does not.
You're right, there is a jump, however, that's not why we wouldn't include 2.
The limit is.
Scroll just above. Look at that definition of continuity at an endpoint. Yeah, so the limit as x approaches 2 from the left does not match the function value at x equals to 2. The limit as x approaches 2 from the left is not equal to the function value at 2. And that's why we are not including 2 in that interval. Same reason when we go to the next interval. We are not going to include 2 because as x approaches 2 from the right, that limit does not match the function value. So we're not including 2 here. And then we trace, and we see as x approaches 5, the function seems to be approaching infinity, which means, do we include 5 or no? Nope. Okay, and then same reason, as x approaches 5 from the right, the function is approaching negative infinity, so we'll go from 5 up to 6. Do we include 6? Yes. Why? Not from the right, from the left, matches the function value at x approaches 6. Do we see that? So this is what it looks like when the left-sided limit matches, and we're considering the right endpoint of the interval. So the fact that the left-sided limit as x approaches 6 is equal to, was that 2? And then the function value is also equal to 2 at x equals to 6, means we can include 6 in the interval. We can say the function is continuous at 6. Okay, to continue on, we're not going, or we'll keep talking about it. Okay, so then from 6 to, what was that, 8? 6 to 8, we have to lift our pencil. We wouldn't include any of those endpoints. Do we see why? Function value wouldn't match limit value. What's the next interval? 8 to 10. Also not including endpoints for the same reason. Limits wouldn't match function values at the endpoints. And then 10 to 11, same thing, not including. And then 11 to infinity and beyond. No. Okay, x values where there is a removable discontinuity. Malika, what'd your group end up with for removable?
Wait, removable? X equals 8 and x equals 10.
Do we all agree with that? So looking at 8 and 10, well at 8, the limit value, the two-sided limit, would match the function value. At 10, the function's undefined, but the limit exists. So both being removable, and then, Gabby, can you tell me where you guys determined there were non-removable discontinuities?
X equals -2 to 5, 6, and 11.
Okay, so at -2, it looks like the function increases without bound from the left or right side of -2, which indicates there's a vertical asymptote. Even though there is a point there, the function is increasing without bound from the left and the right side. So that's a non-removable discontinuity, which we'll talk more about in section 1.5. At x equals to +2, we see the one-sided limits both exist, but they're not equal to each other, causing the jump. At x equals to 5, there's a vertical asymptote again, so that's another section 1.5 we'll talk about more. At x equals to 6, one-sided limits are equal, both exist, but they're not equal to each other, causing the jump. And then same thing at x equals to 11, right? There's the jump in the graph. Questions? Let's keep going. Okay, in the same groups that you were just in, why don't you take a little trip down memory lane and sketch the graph of this piecewise function. Maybe you need to pick each other's brain in order to do that. Remind yourselves, yeah, you could use a sticky if you heard somebody say something about a sticky. I'll use a sticky. I'll make it look nicer, huh?
Definitely not. Is this in like a recent notability?
That cat was like, I mean, that yacht was like a cat. It looked like a cat thing.
Two. You could hit it with the.
Wait, there was
the x minus four. It's x minus one squared. So there's a whole at x minus
What's this?
check with the negative 2x minus
Which one is that if it would like combine it to turn to x minus 1 squared?
Yeah, which is
X
how do you
minus
graph
2x
x squared minus 2x
Because negative 1
Plug
is
in,
negative.
plug in the x.
What do you mean plug in? Literally just plug in.
Like plug in the x.
Plug and.
Like,
Plug in.
It's not, does not even
4
combine.
minus 4.
It's just one. It's just 1 to 3 jumpies, and then it's like an open circle. So if you put one, that's like the middle.
Where's the, you know, satisfying x?
Yeah.
There are different thoughts you could use for determining the graph for that middle piece. You could just think about plugging in values if you wanted to, and recognizing at the end point you would have an open circle, or you could have completed the square and rewritten x squared minus 2x minus 1 over x squared.
When they talk about naming their, when they talk about naming their kids, they're like, yo, what's the deal with
Okay,
storage?
1 more minute. Figuring out what your graph looks like. Take a little trip down memory lane.
This one looks better. Which graph looks better? He's saying absolute value of x looks better than x cubed. This one looks more satisfying than just absolute value, right?
that's all curvy. Look at this.
No, that's it's smoother though.
Yes. No. That's not the point.
So for like x is equal
It's
to
almost like a personality. It almost says something about your personality, right?
Yeah, I think so.
I'm just doing substitution now.
Wait, who needs horoscopes?
What are you doing with the L line?
What does that mean?
What's astrology? What's your star sign now? What's your favorite graph?
All right, you guys, do we have a sketch?
Actually, I think we've done this before, like, what type of,
We've had a number of things, yeah, like
Yeah.
what type, yeah.
Ian would be
Totes.
probably like, I think he'd be tan X.
Alright, a couple, like the first part, so x squared, for x less than or equal to 1, that one's pretty straightforward. You could choose, so to graph x squared minus 2x minus 1, you could have either completed the square and then thought about like, oh, the vertex, or like x squared being shifted to the right 1 down 2. That's the way I kind of thought about it. But the fact that x is not included in the endpoints of this interval, so like 1 at x equals to 1, there would be an open circle point for that piece of the graph, and then same thing with x equals to 3. And then the horizontal line for y equals to 4 for that last piece whenever x is greater than or equal to 3. Did we all come up with something that was kind of like this, resembles this? And then, right, like, or you could have thought about like taking into account those domain restrictions and then just plugging in x values to get points. Like that also would have worked fine. Okie dokie. So let's identify the intervals where f is continuous, not just from reading the graph, right? Like that's like how we would have done it before, but that's not really like a true justification for identifying where the function is continuous or discontinuous. So what we're going to do is, looking at this piecewise, we're going to focus in on where there are potentially points of discontinuity. And then the reason I had to graph this is we're just going to like double check to make sure that everything we come up with makes sense with the graph that we are familiar with. Okay. So let's focus on x equals to 1, and we're also going to think about focusing on x equals to 3. So the first question we're going to be thinking about in our brain is focusing on x equals to 1. More specifically, is f continuous at 1? And like obviously we already know, no, it's not continuous, right? Like based on prior knowledge. But using this definition of continuity at a point, we go, okay, f of 1 would be 1. Do we all see that? So if you hadn't already sketched the graph, you might be like, oh yeah, f could be continuous at 1. That's cool. And then because this is a piecewise, we're thinking one-sided limits. So the limit as x approaches 1 from the left. So that's thinking values to the left of 1. That would be that first interval. We plug in 1 there and we would get 1. And then if we think about the limit as x approaches 1 from the right, values to the right of 1 would be in that second interval. And I realize that the last interval is still values to the right of 1, but remember, when we're thinking about limits, we're thinking about in the neighborhood of 1. What's happening? Like directly to the right of 1, which would be in this interval. So then plugging 1 in here, we would end up with -2. And then we could conclude that, well, since the limit as x approaches 1 from the left of f of x is not equal to the limit as x approaches 1 from the right, the limit as x approaches 1 is dne. And then I don't remember if it was on the most recent assignment or if I was like imagining things. You guys, you can't just say lim as x approaches 1. Like you have to say what you're taking the limit of. Because this is a piecewise, you can just reference f of x, right? F of x has been defined on the page. So you can just say f of x. You don't need to write out the rule or anything again. Because that limit is D&E, we can say or conclude that f has a non-removable discontinuity at x equals to 1. I got a page here just so I don't run out of room. Okay, so then next focusing, is f continuous at x equals to 3? Well, no, we know it's not. But like using the definition, practicing using that definition of continuity at a point, you're thinking f of 3? Why, that's equal to 4. And then one-sided limits. As x approaches 3 from the left. That would be that second interval, we get 2. And then the limit as x approaches 3 from the right. That would be the last interval where we get 4. So we can say, again, something like since the limit as x approaches 3 from the left is not equal to the limit as x approaches 3 from the right, the two-sided limit is D&E. And therefore, f, again, has a non-removable discontinuity at x equals to 3. Putting all of that information together, we could also conclude, in conclusion, f is why do I have such a hard time spelling continuous? Is continuous on the intervals. So from negative infinity to 1, would we include 1? Well, 1 is the right endpoint, right? So if we're thinking about 1 approaching from the left, okay, we get 1. Ooh, I didn't mean that. 1 approaching from the left, we'd get 1. The function value at 1 is 1. So, hey, those values match, meaning we can include 1 here. Which means we can't include 1 on the next interval. That wouldn't make sense, but you could always double check. And then up to 3, and we go, okay, well, 3 is the right-sided limit. The limit as x approaches 3 from the left is 2. The function value would be 4, so nope, we're not going to include 3. And referencing the graph, that should make sense too. But then for when 3 is the left endpoint of the interval, so thinking from 3 on, we go, oh, there's a different color here. 3, x approaching 3 from the right is 4. The function value at 3 is 4. So, yeah. we would include 3 to infinity. And beyond.
So about what the piecewise function works?
So, okay.
Like, so it has something equal to 1, so you include 1, and then to some include 1, so you don't include 1.
Well, that's not why though, right? It's because of the one-sided limit values, like whether they match the function values of the endpoints is the actual why. Like if you were justifying. Yes, if you were eyeballing a piecewise and you're like, oh, if the endpoint is included versus not being included, then yes, that is something that you can take into account. But that's not what you would use to explain. Like if you're being asked to justify, you would need to fall back onto definition of continuity at a point. See, it says, and justify using definition of continuity at a point. Okay, questions? We're out of here at 38, I think. So properties of continuity are pretty straightforward. I don't know if I'm going to go through this kind of quickly. This should feel very like deja vu. But basically, if you're thinking about functions being created from other functions again, and if the functions that are the parts of the new function are continuous at a point, then these functions should also be continuous. And really, this question, so what functions that we previously studied are continuous at every point in their domains? Not continuous everywhere necessarily, although we could then identify that subset. But really, aren't all of the functions besides piecewise functions continuous at every point in their domain? So like we could right now just kind of make a catalog of all of the functions you guys have studied. Which is kind of crazy, right? So we've studied polynomial functions. We've studied rational functions. We've studied root functions. Right, like square root, cube root. Exponential functions. Log functions. So logarithmic functions. We've also studied logistic functions. Remember those? Those were fun. Okay. Trig functions. And their inverses. So the inverse trig functions. Now, which of these could we say are continuous everywhere? And when I say continuous everywhere, we mean from negative infinity to positive infinity. Which of these, from this list of functions, do you guys recognize as like a characteristic of those functions, them being continuous everywhere? Exponential functions are, yeah, totally. What else? Just because we didn't spend that much time on them, I'm going to put it here. Logistic functions. Logistic growth functions.
What's a logistic function?
When there's like a limiting factor, so like the growth starts out as almost being exponential, and then there's an inflection point where it kind of levels off. The growth levels off. Some, not all, but some trig functions are continuous for all real numbers. Do we remember which ones?
Cosine.
Sine and cosine. And then for the inverse trig, arctan. Okay, but just kind of keeping that in mind for then whenever we're thinking about like creating functions from other functions. So like if we were thinking about having these two functions, which first of all, f, cosine would be continuous over all real numbers. G of x would be continuous over its domain, which would be from 0 to infinity. I know I'm going through this pretty quickly. I want to get to one more type of problem. So like 3 times cosine x, well, that would be continuous over all real numbers. If we're thinking about a function created from f plus g, well, we could think about the intersection of those two intervals where each function is continuous, which would just be the interval for this one from 0 to infinity, and so on. Like this would also be 0 to infinity. And then for when we think about taking the ratio, we would just exclude 0, right? Because 0 would make the denominator 0. I am going to skip over continuity of a composite function. It's kind of the same as like last year when we studied determining domain of a composite function. Like same idea. If you know what the rules are, then you could just think about, well, what is the equation of the function and determine continuity from there. So I'm going to kind of skip over this one, but we'll revisit at the beginning of next class. So again, skip to Malou. These ones are fun though. So this last type of problem that's in this set of notes is a type of problem that would like definitely come up, probably as a multiple choice, but could potentially come up as like part of a free response question. So we're going to consider the following piecewise functions and determine the value of a and b such that the function is continuous. This first one, there's no b, but we're looking at this piecewise where each piece is linear, right? Like the graph of each piece would represent a line. And over all real numbers, each piece would be continuous. But because it's a piecewise, there could potentially be a point of discontinuity where this interval switches, right? Where the domain of each piece switches. So if we focus in on 2, and this is not necessarily how you have to show work, but I'm showing you like you should be thinking about the definition of continuity at a point in doing these problems, is that if we were to think about applying that definition, and we're going, okay, well, g of 2 would be 2 plus 3, which is 5. So don't we want the limit to match the function value for the function to be continuous? Like we would want the limit as x approaches 2 of g of x to be equal to 5. So then we think about, well, what would have to be true for that to happen? Since this is a piecewise, we would normally think one-sided limits, right? So as x approaches 2 from the left, we would get 5. And then the limit as x approaches 2 from the right, we would get 2a plus 6. For the two-sided limit to be equal to 5, what would have to be true? Yeah, 2a plus 6 must be equal to 5, or 5 must be equal to 2a plus 6. So that means that a would end up having to be equal to negative 1/2. So in the groups that you were working in earlier, can you guys try B? Again, you don't have to show like all the steps of using the definition of continuity at a point, but you should be thinking about it as you're figuring out how to solve for A and B. And guess and check is not, I will put this as a free response, and guess and check is not going to give you full credit. Like, your work should justify why you get those values. Talk to each other, please. Explain what you're doing. If your other group members are stumped, or maybe you guys have different ideas, check in with each other. So you should be
Okay, so you do 2 equals x.
And then
Like
use
for
the
the
elimination.
lower limit, and then you do limit for as x approaches 3. And then you get a is equal to negative 2. Both sides. Oh, okay. Wait, so I have to do it for 3? Yeah, for the limit for 3 on both sides, and then also I need to refill this. I'm gonna start like, can I refill this?
The bell's gonna ring in 2 minutes. Might want to just, want to just wait. Okay, we'll check in just a minute here before the bell rings. Make sure someone could follow your work.
What did you get? A
very wrong too.
Why?
I think I did it.
Wait.
I got -1 and 1.
I did it right, the wrong way.
The wrong way.
What's A and B?
Actually, no, I
And
did
then
it right.
-1 for A, 1 for B.
What'd you do? What did you get? Oh, wait.
B equals 3 plus
Oh,
A.
I accidentally put 2 in.
Oh.
You add, so what I feel like, I took the minus, I feel like you took that -1.
Oh, wait.
Did-
How did I
did-
put a
or is that
minus
wrong?
one
So
there?
get rid of that -1.
Okay, why are you talking like that? What's wrong with you? Is it?
Round upside down. Turn that round.
So you guys, we're gonna spend a little bit, you do have homework from 1.4, do the best you can, and we're gonna wrap up 1.4 at the beginning of next class before we do 1.5, which is a short section, and it's going to feel very, very, very familiar to you. Don't forget to turn in your quiz.